as they say in Monty Python, and now for something completely different. More particularly, the origins of this discussion session came from, well, Samir and I started having discussions about the many and multiple claims coming from wormholes and islands and so forth about having solved the information paradox or having made great progress and so on. And Samir and I were Zooming roughly once a week from quite a few weeks in the fall, trying to figure out what was being said and the progress is very challenging. So the purpose of this exercise is really to sort of extend that discussion to involve the audience here. So the plan is that Samir will talk for about 10 or 15 minutes, just introducing the issues, and then start through, but please jump in if there are questions in the middle of it, but Samir will pause in about 10 or 15 minutes in, and then just start asking questions or start engaging. But it's meant to be a conversation, a discussion. But Samir is going to try and catalyze that discussion by making pieces of presentations as we go. One other thing, we'll lose our tech support fairly soon, and so if there's a discussion and writing, it needs to be on this side of the board, and hopefully things will work fine. Anyway, Samir.
Thank you. It's a great pleasure to be able to have a discussion on things which have been confusing me very completely for 4 years now. So I hope that you will be able to clarify things for me. I want to be sure I know how to work this. Do I just press buttons? Okay. So I'll just begin by introducing the information paradox and the issue just to set notation. I know everybody knows this, but just because we want to have the same notation for everything that everyone says, so just recalling what the information puzzle is. And is this the pointer? Okay. So we all know that this is how you make a black hole. You start with a star, it collapses. At some point, the light cones point inwards inside the horizon, then it can't resist collapse anymore, and it makes a singularity, which we'll just schematically write as something in the middle, and then we get the horizon. Okay. And nothing can stay at the horizon because the light cones point inward, so it's very hard to, you can't possibly stay even just a little bit outside, and once you're inside, you will fall down. Given the structure of light cones at the horizon, something just outside trying to head out does ultimately manage to escape, but something just inside, even if it is trying to head as much out as it can, it really ends up falling in. So the geodesics around the horizon, they sort of spread out. They split away from each other, and so a Fourier mode straddling the horizon gets stretched. And once the stretching goes to the nonlinear regime, a vacuum mode here basically becomes a pair of entangled particles. I call this one B and this one C, and you can schematically write the entanglement as if both were in the vacuum, 0, 0, and then plus 1, 1. Of course, there's also a place 2, 2, and 3, 3, and so on, but you don't really care because it's just the fact the entanglement is order 1 per pair, which is the source of all the difficulties that we have. So this was way back Hawking 1974, but that's where the entangled particles are coming from. So the entanglement keeps rising, and as we go through emission steps, the entanglement just keeps going up, and all the way to the end point where you have this well-known puzzle. If the hole completely disappears as Hawking had assumed, then the radiation is left in a state which is entangled, but then nothing it's entangled with. So that's a loss of quantum unitarity because now you can't write down a wave function for these guys. And if you assume it gets left in a small remnant, well, remnants have many problems of their own, and ADS safety doesn't seem to allow them anyway, so we don't talk much about remnants in string theory. Just to contrast that with how normal bodies behave, if you take a piece of coal and burn it, and if this is an atom which emitted a photon, well, the emitted photon can, in general, be entangled with the atom which is left behind, can be spin up, down, minus, down, up in the emission. But after a while, since we are going to burn the coal away completely, this atom also floats out like some kind of ash, and then the things at infinity are all entangled with each other, and so there's no problem if the vacuum is left behind here. So in the beginning, the page curve, this is called the page curve of the entanglement as a function of time. In the beginning, you can see it's going up, but when the remaining bits are also coming out, you can see it's going down. So the fact the page curve of the black hole is different, well, that is the whole problem we are trying to solve. And again, just to emphasize where the difference comes from, in the coal, the radiation is coming out of the objects that make the coal, and in the Hawking case, they are coming out of pairs pulled out of the vacuum. It's more like the Schwinger process, and that's why the two page curves are different. So people have tried many things with these in the past, but of course, many things were tried and didn't quite work out. I just want to mention two of them because shades of these things are still involved in the things that people are saying now. Okay, so just good to know what people said and exactly what were the reasons for which they didn't work out. So one was the idea of complementarity that was proposed by Tuhuf and then taken much further by Susskind and his collaborators. And this said there are two descriptions of the black hole. In one, an infalling observer sees just the vacuum around the horizon, so it's just a normal picture of the black hole. But there's another description in which there's a stretched horizon around the black hole, and anything falling in just bounces off that and scatters off in a mixed up way from here, but just scattered away unitarily. And so you save your information, and you also save the fact that you have the classical physics, you just go in. So you have two different descriptions of the black hole, but immediately people should ask, how can this be? I mean, how can you both go in and bounce out? You certainly can't be in two places by quantum cloning. And more precisely, like, what would cause you to bounce anyway? Because in a good slicing through the horizon, you're saying that across this point you bounce off, you never end up going inside in one of the pictures. But since everything is completely smooth space-time, what is the logic which tells you where to put this particular boundary? What is different from the usual case? The whole problem with the horizon is not a special place, so how do you come across these rules? And the rough argument those days was, if two regions, this and this, can't communicate with each other, somebody here can't talk back to somebody left outside, then maybe it's okay to have quantum cloning between the two. So it's some kind of new physics principles which were being introduced. But there was an immediate problem with this. One can make these nice rules, but you should go back and ask what happened to the original puzzle. So you should go back and ask, in one of the descriptions, the horizon was a smooth place. So in that description, you will again get the entangled pairs. And so in that description, the entanglement will keep rising. And so what have you done? And so this puzzle was always there, and people kept asking Lenny about it. I know that I did. But there was never any answer, because somehow they were not really thinking about the entangled pairs at all. But again, this issue was looked at more carefully by AMS in 2012, and then they did show, look, the page curve goes up, so it doesn't work. And so that's why it essentially collapsed. There were other parts of AMS which I believe were incorrect. We wrote a paper about that. Infalling object doesn't have to feel a firewall. We made a bit model where it doesn't feel a firewall. But those are not relevant to the questions we are discussing today, so let me not focus on that. But important thing was complementarity did not work like an idea, because it was more like a wish list of, I want information to come out, so let's put a stretched horizon. I also can't find any way to stop things from falling in, so I want a picture where everything goes in. So if you want to just have both, you can sort of make a wish list that, okay, I have both. And then you put a new idea that sometimes you can get quantum cloning, but there weren't really any computations which one could really do, at least at that time, to back it up. And so in the end, I think it didn't work out. But the other thing which didn't work out, which is also visible in various guises in what people do right now, is the idea of small corrections. And this was there in many, many guises throughout the story. So let me just say a bit about that, and then that's all I'm going to say about the history of the problem, and we'll do the open questions. So what's the idea of small corrections? Well, since people couldn't find any way to change the black hole geometry, and the reason you can't change it easily is because at the horizon, everything is semi-classical physics, curvatures are so low. So if we keep this geometry, and then we have this pair production problem, how can we ever get out of it? Well, one possibility is that if you looked at the entanglement of the particles produced with their partner left behind, Hawking did a leading order calculation where each particle is entangled with its partner by, let's say, log 2 in the model we made. But there could be some small, subtle quantum gravity effect that create correlations between all the other particles as well. So those would be very subleading. But the point is there are a large number of quanta involved in the problem, roughly m over m Planck square. And so by the time you add all the subleading corrections, perhaps the entanglement story is not what Hawking found, but that the page curve actually goes down. So let's just be a little bit more precise about this and see why that didn't work out. So the leading order answer looked like this. The two members outside and inside were connected as entangled as 0, 0 plus 1, 1. And what does it mean to put small corrections? Let's try to write it more explicitly. You could say, let's say the second pair which is emitted, B2 and C2, if at the first step, the pair B1 and C1 were in the state 0, 0, as opposed to 1, 1. If they were in the state 0, 0, in the second pair, I don't make them exactly 0, 0, 0 plus 1, 1. I can maybe have a little bit more of 0, 0, a little bit less of 1, 1. On the other hand, if the first pair was a 1, 1, I have a different amount of 0, 0, and 1, 1. These epsilons are small because I have to keep close to the semi-classical picture, but you can see I have now correlated the second pair to the first pair, because what happens to the second pair here or here depends on what happened to the first pair here or here. Okay, so these are subtle correlations you can introduce, and these epsilons can depend on anything. They can be chosen arbitrarily, so you can put arbitrary correlations. And you can see that after n steps of emission, there are 2 to the n correction terms. And so it's not unreasonable to think that if you have even exponentially small corrections, because the number of terms is exponentially large, perhaps by the time you are done and you compute the entanglement of all the outside with the inside, this guy just goes over to this guy. Well, if that were true, it would be really nice, because then there was no puzzle to start with. There can always be small subleading corrections to something, and if that takes care of it, then there wasn't anything to worry about. It turns out you can't get away with that. Somehow, even though people proposed that, nobody actually ever checked that they could choose all these epsilon 1, epsilon 2, and so on in a way that the curve would come down. Okay, so you should try to make at least one toy model, even if it doesn't have a source, to put those numbers to see, can you get it to come down? It turns out it doesn't matter how you choose the epsilons, or in fact, even if you make some other model around it, it can never actually come down. So the small correction theorem says that if this one is corrected to this plus a small correction, and the correction is small in the sense is bounded by epsilon, but can be anything, that you can correlate with anything in any way that you feel like, that the entanglement at every step must keep growing like this. This is the entanglement you get in Hawking, and you can reduce it slightly because of the corrections, but only by this amount bounded by 2 epsilons, so the entanglement has to keep going up. Okay. So this tells you that you must have an order unity correction at the horizon. Any small correction to the dynamics is not going to help you, and in a way it helped explain to people why it would be a good idea if one could get fuzzballs, because, well, the fuzzball idea in a nutshell is that instead of the horizon, the whole thing gets quantum corrected, and then you actually have corrections of order unity at the horizon. It's not semi-classical dynamics in any approximation. And so you say, well, that of course solves the problem. It's more like a star. But initially, many people were opposed to the idea because they felt this was too big a correction, and only a few odd states might be fuzzballs. The others might still be sort of like this. But the small correction theorem sort of comes and sort of completes the fuzzball thing. You create some fuzzballs and show them as examples that you can break the no-hair theorems. But then these other, the small correction theorem tells you, you actually need that, and otherwise you have a problem. But then after that, people started saying, over the last few years, maybe from about 7 or 8 years ago, okay, let's agree that every microstate is a fuzzball. That somehow makes sense. And a lot of that happened because a large number of new states that were being found by the people like Nick and Joseph and Emil and David and so on. So there were so many new states coming up that many people sort of got converted to saying every state is a fuzzball. But the new idea was that perhaps we don't really need the fuzzballs. The fuzzballs are a microscopic description, perhaps at the Planck scale of what the whole is doing. But if you want the low energy dynamics, it's perhaps still given by usual semi-classical physics. So the idea for that would be that, just trying to draw it out like this, the full exact theory is some quantum mess, and what you radiate is some quantum mess, everything is very quantum, but then there is a code subspace or an EFT, effective field theory approximation, whatever words you like to use, in which you can see the whole process as if there was semi-classical dynamics. It wouldn't come out exactly. Again, there can be small errors. Of course, we should allow that. But there's some approximation with the entire process of radiation from this complicated mess is basically given by the Hawking process around here. If that were true, well, again, it's fine. You have to not show that everything is a fuzzball, and perhaps with enough effort you can. But it would mean that the Hawking process and all the questions you want to answer can still be somehow understood through semi-classical physics. Unfortunately, it turns out this is not possible. And this is proved by the effective small correction theorem, which is sort of a small extension of the small correction theorem. And that theorem says that, suppose in the exact theory, the black hole evaporation is unitary, and that everybody seems to want. And there's an EFT approximation that gives semi-classical dynamics whenever there's low curvature regions. So you have semi-classical all the way here, just breaks down here. Then the exact theory that you started with must have non-local effects across arbitrary large distances, which means you flip something here, it's going to flip something here. Okay. This is making some sound like clicks. Is that supposed to happen?
What should make the sound?
If I press the... Okay. If it doesn't bother you, it's okay. Okay. Okay, so this is all I was going to say, that the reason the small correction theorem and the effective small correction theorem are not perhaps fully absorbed in the consciousness of everybody working in the field is because they both rely on the strong subadditivity of quantum entanglement entropy, and that is something which doesn't have an intuitive proof. Okay? It requires, there's a lot of 10 pages of calculation at the end of the textbook, which will establish the Lieb lemma, and then from there you get the theorem. So, but just to emphasize what this is, it says that often you hear the fact that the actual black hole is like a piece of coal in the exact quantum gravity theory, so that's called the central dogma. But then somehow at low energies you would make a EFT approximation and some combination of those bits, and you will get this kind of physics. But actually you can't do that. And if you try to do that, the penalty you'll have to pay is that there has to be non-local effects in the exact theory, not the semi-classical theory. And then you have to go back and ask if that's okay with you in string theory. Okay? So that's where we are with this. There was a question there.
I just wanted a small clarification. What does non-local effects mean? Like, are you thinking of entanglement or
so not entanglement?
Hamiltonian?
I'm glad you asked that again. Not entanglement.
Or Hamiltonian.
Hamiltonian.
Or
Hamiltonian.
Okay, and also what type of operators can you?
Yeah. So they're exactly of this kind. Entanglement is not a non-local effect. I mean, that's just quantum mechanics. So let's not call it a non-local effect. Okay, even though it's all the EPR stuff and all is confusing, but it's just normal physics. It's a Hamiltonian interaction is what you would need. That if you take spins here and you make an operation on it, doesn't have to be simple. It can be complicated. It can involve all the spins that have been emitted, right? So you can take 1,000,000 spins here. But if you do something sufficiently complicated on the spins, but arbitrarily far away, you can change the state of what is here. Okay. So it's the arbitrarily far away which is the problem. You make a black hole of mass 1,000,000 Planck units. Let's say you evaporate half of it and you have collect those bits and take them as far as you want. Then you have this problem.
Just to play the advocate of the wormhole paradigm people, it's not just that you flip something at R goes like m cubed and something is flipped in the interior. They're saying you have to do something sufficiently complex at R goes.
And that is agreed. I already said something complicated. You involve 1,000,000 bits here. If you take something very complicated far away, the question is it okay with you that if I flip something very complicated, that's why I said take a black hole of 1,000 Planck masses, it emits 1,000,000 like n square bits, you have 1,000,000 bits, but arbitrarily far away. So distance can be infinite. And now when you flip these guys, you're going to flip something there. If that's okay with you, you can look for models like this. So in this paper, we actually did make bit models which do this. I mean, I'm not saying that string theory does that, but that's the penalty. One has to understand that you cannot get away from there. The other thing I want to mention in that regard is that what it does is that it changes observations made to the black hole from outside. So if I do a complicated operation here, if light was able to flee through the horizon now, I do that complicated operation, it's going to reflect back.
Oh, is it?
So I was talking to Juan and he said that does bother him because he thought it would only change things inside, but you can actually prove that what's happening is observer will reflect light here if you make a change here, while before that change it was not reflected. So that's the precise statement of what would happen.
Okay, maybe you have already answered my question. So the non-locality actually means non-causality.
Non-causality?
Causality.
Yeah, I think they're closely connected. People sometimes distinguish them, but let's agree with that. I'm good with that.
Okay.
Yeah.
Okay.
Yeah.
That was also my question. I think that's important because violations of causality, I think that they are much more serious than violations of locality.
And that's true. So yeah, so there is a difference.
So do you claim that there's a violation of causality? That that the islands?
No. So I wasn't talking about causality here. Good. So let's be more precise, because it's true that when this is radiated and I go very far, I collect them and I'm sitting with them.
Yes.
Now I can wait for time to pass, because I haven't talked about how much time has gone. Maybe light has had time to come and go. Light has had time to come because these guys came out at the speed of light. So light has had time to come. So we're not talking causality. But now we are talking locality. I'll pass these through a complicated Stern-Gerlach. And what will happen is, if earlier light was falling in here, now light will just bounce off from here. So I take two identical copies of this experiment, identically prepared. In one I do something here, in the other I do nothing. In one case, an observer here sends a signal, it goes in. In the other case, the observer sends a signal, and he gets the light flashing back. That's the problem. If that's okay, it's okay. Then we can go and see whether string theory can do that. Okay, so that's what the theorem said. That's what the paper has. Another question back there? Oh,
Yeah,
Emil.
so So there's one effective entanglement, which is that if I'm looking at some Hawking quantum very far away, it's definitely entangled with something behind the horizon. And if I measure the Hawking quantum, say its polarization state, then the fact that the Hawking pair was created in a unique state and represents only basically a single qubit means that when I measure the Hawking quantum far away, I've simultaneously measured some property of something behind the horizon.
Of course. That's
So
normal ER equals EPR.
That's not acausality, non-locality, or anything.
That's
it's
neither.
just entanglement.
No, that's just entanglement.
And so, so that's okay. So that's clarification number one. Question two then is the sort of thing that Roberto was talking about in his talk. Is that if you had, according to his scenario, as I would interpret it, would be that suppose you had the low energy effective field theory Hawking process going on. There's some antiparticle partner which remains behind the horizon, but he would say, well, okay, that's some state on some bag of gold slice that is just some complicated linear combination of the e to the s minus 1 states that are inside the black hole left behind. And so the problem with the Hawking, after you emit many Hawking pairs, is that eventually the Hawking quanta have to start getting entangled with each other rather than what's left behind in the black hole. So that can be accomplished if there's some mechanism by which you say this C partner is secretly some complicated rewriting of the degrees of freedom inside the black hole. Is that what you would call an order 1 correction?
Okay, so let me try to repeat what you said in my language and see if I understood the question. So indeed, the idea of this picture was that firstly, in the old bag of gold story, I want to see, let's get the language for that clear. In the traditional bag of gold story, it's like a remnant. There are infinitely many states inside here. Let's agree we don't want that, right? Those states have to have dot products in this bag of gold language, so there are only finitely many. For the rest, once that's okay, there are only finitely many states here in this mess. This C is indeed supposed to be a linear combination of these bits, okay? And the bits at infinity. The effective C which is coming here is supposed to be made as some complicated linear combination of the bits which are here and the bits which are here. And the corresponding B is also made out of some bits here and some bits here. So the claim is you take any unitary process where you have bits B and C and the page curve goes up and down, just write any model you want. Now you define a B out of any set of bits by using any linear combination of these. You define the C by getting any linear combination of these. You want the B and C to do the usual thing that you want them to do, from the vacuum to evolve into this pair. Okay? In that theory with that Hamiltonian that you had, I will find that if I flip these, I change the dynamics which I can observe here. That's the claim. I'm not giving you a proof here, so I can't prove that, but just to be sure what the statement is, you make me a model of a unitary evaporation where the bits come out, where we can make any complicated combination, and it's up to you how you choose it, of the bits here and here to make B, and similarly some bits here and here to make C, which respect that property. This model has to have the fact that a complicated change here will change the reflectivity of light of this object. That's the claim. So the proof is not here, so I don't know what else to give you, but is the claim clear?
The claim is clear. I remain puzzled by the claim because the sorts of things that have been said recently are that some state that you thought was some independent C quanta behind the horizon, which wasn't really related to anything else in the black hole interior, secretly can be rewritten as some complicated combination of the remaining qubits inside the black hole. And that's the thing you want. You want the B quantum to be entangled with the black hole remaining left behind. And
so,
it's
I think this
microstates.
So that's what you want. I think the point is you can't just jump into what you want and have it. And I can try to say why you don't get it. Maybe I can try to say roughly why you don't get it. So what happens is that what you're trying to mirror in this picture is that a couple of states which are entangled with each other like the vacuum just become these B and C, right? So the point is these two things make a unit which is not entangled with each other. So you have to find something in this region which started off with zero entanglement with each other, right? because that's what we have written over here. They're entangled with each other, but not with anything else. Because if the two bits are entangled with each other, they can't be entangled with anybody else. So you can make these bits, suppose you made it out of something here and something here. When these two pieces split apart, part of the stuff is here and part of it is here. If you change the bits here, what happens is whatever helped you to define the vacuum dynamics there, that state is no longer the vacuum. So if you try to make some effective projection of a code subspace which gave you the vacuum in this region, if you change the spin of the bit outside, whatever rule you had for getting the vacuum over there, it doesn't give you the vacuum over there. So suppose your rule was the low energy semi-classical vacuum of that region comes from a bit here up plus a bit here down plus a bit here down, a bit here up, and now you flip this bit. Then the state there, instead of being the vacuum, becomes something orthogonal to the vacuum. And that's the problem. You bounce off it. It's not the vacuum. So you want to entangle these two guys across the horizon in a particular way, as AMS was also arguing all the time. And if you make the bits out of things here, you change this bit, then these two effective bits are no longer entangled in the way that will make the vacuum.
But you only care about that in the process where they're near the horizon. Once they're separated far away, you
Good.
do this one all you want. You're not changing the vacuum structure near the horizon.
Can you repeat the statement?
That Emil made.
Yes.
So Emil is wondering about the fact whether all the complaints I'm having near the horizon remain valid when the B starts floating further from the horizon. Yeah. Okay. And nothing much happens at that step, because when you try to break up the semi-classical thing, I take a domain, let's say all the way up to 4M, and I say everything in there, let's try to make out of bits from here and here. So up to the time this gets up to, let's say, away to 4M, everything I was saying before holds. But it is assumed in the proof of the theorem that once this object, which is out to 4M, the quantum mass out there in the first picture and the effective mass here, they are the same up to order epsilon, because outside, if you assume that nothing happens but EFT, then there's no new physics outside. So if this bit changes from what spin it had between 4M and infinity, that's different. That's a non-local effect outside the black hole. So I'm assuming once it gets out, no change. Then there's no difference between it getting far out and here. But maybe I should just move on, because I can't actually give the proof of the claim. I just want to state the claim here.
Look, I had a question.
Okay.
Can you explain a bit more in what context you did the calculation that shows that light reflects? If you did it in the context of the replica wormholes, I don't see why light would reflect off the horizon.
No, nothing to do with replica wormholes. No.
Well, that's the context in which the calculation was done that showed that the page curve, is correctly obeyed. So I think one should do it within the same context to make sure that.
Let's talk about, when we come to replica wormholes, I have too many confused about that, but we can talk about that too. This was just about a bit model. It's an explicit claim that if you sit down at home and try to make a model with 100 bits here, 100 bits here, they're evaporating out, they go out. You make any model like that, and you wanted to have the property that they're entangled like this at each production step coming out of some local Hamiltonian, then you will find this property that if you change here, if you try to make the vacuum by some rule out here, the state there will no longer be the vacuum because you've changed the state. You need a definite state there, it won't be that state. So whatever state you want, which is the correctly entangled state across in terms of bits, it's just a property of quantum mechanics and bits. If you demand a particular bit entanglement here, if you make them out of these, if you change these bits, the state won't be the same state. So
and maybe just to clarify, regardless of the resolution, how one would resolve this paradox or not resolve it, you would say that this also happens in ADS-CFT. That if I have an evaporating black hole and I capture the radiation at infinity, then I can make light bounce off a black hole in the bulk.
By changing the radiation outside.
By changing the radiation at the boundary.
You can make black holes in ADS, and you can. I can't distinguish them. Absolutely. Okay, so that's all I was going to give you as an introduction. And so let's go back to my confusion. And so basically what happened was I tried to learn a lot from the papers that people wrote. So I read over 100 papers over the last 4 years. But I couldn't extract any one thread from top to bottom which would teach me something new about information, okay? I really love to learn anything I can about black hole information. That's what I've been thinking about for 30 years. But I couldn't extract anything. So that's my fault. But I'm hoping that all of you guys can help me extract one clear thread of a result which I can present in a course that I teach on string theory, okay? But when you teach a course, there are students sitting there and they will ask, why is that true? And normally when I teach a course, I always know the answers. But this time, I just can't write down a proof from top to bottom of anything which is new. And so all my questions here are just my confusions. And I just want to see if I can get some clarity on them. Okay, so that's the goal. I have got a lot of help from the various authors of these papers. I just want to acknowledge that. People are very helpful in trying to give me answers. But many people, different people told me different things. And so I couldn't get a consistent answer. So this is just a list of my confusions. I'm going to throw them open as questions. And then hopefully at the end of that, I extract something.
I just want to make a comment because you usually say what string theory says, but in most of the arguments that people have been making over the last few years, there's no string theory.
I agree.
It's a gravitational path integral with some rules. And that's something that that's much, well, I mean, stronger
I have a
or
problem
milder
with those
assumption
rules.
than string theory.
I'm just going to ask you about those rules, absolutely.
Okay.
Because I think those rules have the same kind of difficulty that happened with complementarity of Susskind. We just came up with rules. We didn't challenge them enough. We didn't think about them. In particular, we didn't put them back in the context of pair production enough.
Yeah.
And when you do that and go back and say, what are we really doing? I get stuck. Okay, so that's exactly why we are doing this. I know all of you work very hard in all these calculations, but once in a while, you should also slow down and say, hey, what are we doing? Because that's what happened with complementarity. So that's why I'm asking this question. Let me just begin with something which is very catchy. And I loved this word when I first heard it, ER equals EPR. And my questions are so basic that they really should be asked by undergraduates. So you will pardon the questions. Let's just begin with something very simple. Just consider 2A string theory in flat spacetime. Take two D0 branes very far away at some large separation L. And this is just like two electrons. Let their spins be entangled. Okay, so they have 256 states each, right? So just entangle them. So people talk a lot about entanglement these days, that it has started as something new. But let me just ask this question. Now, this is a theory of quantum gravity. Is there anything I know about entanglement in this setup, which if I took to a condensed matter theorist who doesn't use gravity, is different? Does gravity do anything new?
Any comments?
Okay, does everybody agree it's quantum mechanics? Because some people have told me no. So it's okay to say no. Okay, you can always change your mind in this discussion. You can say something and you can take it back. Otherwise you'll be, you won't feel like saying anything. Does anybody want to say no? Okay, that's good. You can say no later if you want. Okay, so if you say yes, so I guess nobody said no, so I don't have to worry. So we'll forget the yes. Nobody said yes. If there's nothing new here, let me just ask what my undergraduate would ask me. How will this help us to understand black holes? I have a bunch of D branes here. I have one D0, but I can make it 20 D0 branes. I can put some D1 branes and D5 branes. Let's maybe put 1,000 D1s, 1,000 D5s, and whatever. And on this side, 1,000,000 miles away, I have 1,000 D1s, 1,000 D5s. Still nothing new, right? You said nothing new for D0, so nothing new right now. Okay, it's just a bunch of objects with spins. Let's just do it in just states. So ER equals EPR seems to be something which has taught me something new about black holes. Can I learn anything about black holes in this? Suppose somebody asked the question this naive way, what would you tell him? Yeah, look ahead.
Well, I think I would tell them that the calculation in a gravitational EFT in a two-sided black hole agrees with the calculations in quantum mechanics in an entangled system. And I don't think there is a calculation, well, maybe I should ask you, can you show me a calculation in quantum mechanics that would not disagree, that would disagree with the calculation in gravity in a two-sided black hole?
Let me see if I understand the question. Yes, so I have the obvious question for that, right? Because if I take a two-sided black hole, the normal black hole with two horizons, Hawking disagrees, because with that black hole I will get radiation, my entanglement goes the wrong way, the small correction theorem tells me the small corrections can't fix it, it's a violation. So let me just, I had a picture for that, let me just draw the picture. I just take two entangled objects far away. This was just saying what I was saying before. I just have a D1, D5 solution here which just evaporate because for me it's just like a fuzzball, like a piece of coal, there's no problem. Here I have another piece of coal, it evaporates locally, there's no problem. There's no wormhole between them as far as I know. Okay, I don't draw any wormholes. They're just entangled, so the entangled is fine. But then if I drew the Penrose diagram which has the two horizons, the eternal black hole, which is somehow is a wormhole between these two faraway guys, I don't know how to solve the fact that both the horizons give me radiation and the entanglement actually rises. And the small corrections.
I think you're already asking like a question about late time physics, right? You're asking questions past the page time. One first claim is that the two-sided black hole, you can compute correlation functions in the two-sided black holes and compare it to correlation functions in the two-sided state, and they match.
That's very good. And so,
well, that teaches us something.
Good. So I think this is exactly the thing I was trying to extract from the discussion. There are things that work, right? There are effective things that work. You can compute some averages by doing some effective geometries, and all those things will work. What we want to understand is, if you want to compute a two-point correlation of something in two complicatedly entangled objects, which basically may tell you the averages about any one system because you just took two copies to help you understand averages. You can sometimes compute those averages, like in the old work of Shankar using geodesics between them, between the two sides or something like that, and you get the average of a function. These simple things are kind of questions I just want to separate because they tell me nothing about the information puzzle. So my real question is, I want to separate what we have learned, if anything, about the information puzzle questions, the page curve questions like you just mentioned, the entanglement questions, because all those are very delicate questions. You can't know something about the entanglement of something coming out of a black hole until you measure at least half the quanta. If you want to measure the spectrum, the one-point function is enough. But the spectrum is the same for a coal and a black hole. They're both basically thermal. So if something tells me the one-point function or something of two entangled objects, it's a simple question. It's nice to have some way of computing it from gravity, but it's not going to tell me anything about information. So I'm not disagreeing with that. You can compute that. But I just want to keep that question slightly different. Does that look fair?
Sure. Well, not quite, because you asked if you learned anything, and I think we learned something.
Okay.
So from that perspective, it's not fair. But maybe going back to the information paradox, there is maybe a cleaner version in this two-sided setup. There's a cleaner version of the information paradox that involves the two-point function at very late times. This is Juan's version of the information paradox. And that's also resolved by space-time wormhole corrections. So it also tells us, like, there's an expectation that we have for how the two-point function behaves at very late times from the boundary side, because the boundary side is a unitary quantum system. The result in the bulk, in the naive two-sided geometry, disagrees, but agrees once we add to the EFT the elements of these space-time wormholes. And I think that's the simplest setup.
Elements of what again?
Of space-time wormholes. We add topology changing processes to the Euclidean path integral. And I think, in my opinion, that's the simplest setup in which the information paradox was addressed and the information paradox can be posed, because it doesn't involve radiation.
So let me write that down here. Let me write down here things which I would like to understand with great clarity slowly, because it's not like I understand that. But these are things I want to understand. Okay. So let me just write here for the info puzzle. You can add wormholes to prove that. Prove what? Prove that, how should I finish?
To prove that the two-point function behaves like a two-point function from in gravity in a two-sided setup, behaves like a two-point function in a unitary quantum system. It doesn't decay to zero at late times, as the original black hole geometry would predict.
Okay, very good. I would love to learn more about this. So if I can, we should come back and at some point, maybe offline, just see how you start from scratch and actually show something which can actually tell me that it solves the information puzzle.
Okay. Hold on, please. So let me Joseph said that's not enough to get the information out. I'll follow up by saying, are you postulating some long-distance non-locality in the theory? So how's a wormhole going to, it's a Euclidean wormhole. Are you postulating that it has a Lorentzian continuation that's somehow transmitting the information in some bilocal interaction?
No, it's not. I'm not postulating. I'm postulating that the Euclidean answer can be continued to Lorentzian signature, yes? Well, you can get the two-point function in Euclidean signature from the, when you include the wormhole correction, and you can analytically continue that answer. You get what the two-point function is corrected at late times, and that gives you a non-zero, ramp and plateau at very late times, exactly as you would expect in a unitary quantum system for a two-point function.
But the geometry with the horizon now doesn't give you that, right? So you're either implying that the geometry,
the standard two-sided geometry does not give you that. It gives you a two-point function that decays forever. But I was asked what thing that we learned that is new from this program. Here's one proof that I think is very clean and agrees with the result that we get in a unitary quantum system.
the only question was if you have a geometry with a horizon which eats up this thing, the fact that the two-point function doesn't reproduce that, this is an implication that the geometry with the horizon doesn't give you the complete physics. There's some other effect coming on top of the geometry. I'm in Lorentzian. I do a Lorentzian calculation. Geometry with the horizon, information decays. I don't see any deep ramp or anything. Then the question is, there's a Euclidean effect which comes from the wormholes, which has a Lorentzian translation. The question is, what's the Lorentzian translation? I could take the argument to say, great, because I get this information coming out, it means that the horizon is not there, the geometry with the horizon, the Lorentzian geometry with the horizon is garbage, and you get fuzzballs. And I can get the deep ramp plateau from fuzzballs. The question is, why don't I have that?
Keep it simple. Keep it simple. What is the Lorentzian interpretation of the Euclidean wormhole? That's the question I think Joseph asked.
I don't think we know that entirely. It depends a little bit on the calculation that we're doing. When you are asking what is the interpretation, I suppose you have a calculation in mind. Like, how do you probe whether the horizon is still there at late times or something like that?
Well,
I think the interpretation, in my opinion, is that the picture that you have spatial slices that are, well approximated by your GR EFT breaks down at very late times. I don't know, we don't know exactly how it breaks down. It depends on what observable you want to compute. You give me the observable, and we can compute the wormhole correction to that observable. And that should, in principle, answer, what happens at the horizon.
But it doesn't give a Lorentzian mechanism in the sense of, if you've got a wormhole that's 10 to the 67 light years long, which is the evaporation time of a black hole, and you've got all those bits of information, aren't you postulating an insane level of non-locality for Lorentzian physics?
Well, I don't see any specific observable that would probe that non-locality in the wormhole calculation. So if you show me an observable that shows me that causality is broken, or whatever else you want, then I will agree.
So maybe I can say one thing, may ask you one thing about that. Maybe you could still hold the thing without asking your question. So maybe,
sorry.
I find it very hard to make examples where knowing the two-point function, whether it decays one way or the other, would tell me that the evaporation is unitary. So what I'm saying, just one thing, let me just finish. It looks like a one-way implication that you don't want the answer you get from the standard black hole because the two-point function has a bad decay. But unless you do a very, very high multi-point function, normally you can't tell whether something is unitary or not. So you could probably make a lot of models which are equally bad, but where the two-point function has the corrected behavior. So what I'm saying is two-point function maybe is such a crude diagnostic. It's not a good diagnostic of entanglement in a large system. So knowing that a two-point function has this behavior or that behavior may not be telling me anything about whether it's properly entangled or not. So for example, if I give you an example of where the entanglement actually grows, that's an example I often use to check a lot of claims that people make. A normal example in quantum mechanics entanglement actually grows is the Schwinger pair production. So if you just take two parallel plates with charge, plus charge and minus charge, pairs are produced till the whole field discharges. But the pairs are just entangled, and you take the two plates home, you send one plate here, they are entangled by log n. okay, by n log 2. So if you take this example, again, you have lots of states and so on. The same argument should not tell you this time that it's coming out to be a downward going page curve. So I'm just saying that I would love to learn more about the steps here, because I want to be sure that this two-point function is really telling me what I want to know, because I know two-point function cases behave similarly in cases where page curve goes up, sometimes when the page curve goes down. And okay, so it's not a very good diagnostic. But it's an excellent point that you make, and absolutely that's a good direction.
Well, I think the only reason why I brought it up is because it is called Maldesena's version of the information paradox.
So I have always wondered it's too crude. I don't think it's a version of the information puzzle. The puzzle is that the entanglement is growing up, and even if you change the behavior of the two-point function to what you want, I can make you lots of models the entanglement is still growing up. And as long as you have a horizon, the entanglement is still growing up, and the two-point function, I can make it what you want. That was my comment.
So, sorry, can you clarify this thing? You said you have an example where the two-point function does not decay, but the entanglement keeps growing up. Is
no, I'm saying no. I'm not saying I made that example, but I'm sure you can make lots of examples. That's what I was saying.
Just roughly, what's the intuition? You said something.
Yeah, because just a two-point function. I just said to know whether two systems are entangling or not. The page curve part.
Yes.
A two-point function can never give you that information. It roughly requires an
no, I'm
2 to the
asking
n
whether
point
it's
function.
necessary or not. So you're saying it's not sufficient, but I'm trying to ask whether it's necessary or not.
It's obviously necessary because you want it to be like cool. It's not sufficient. Yeah, I'm just saying it's not sufficient, so it's very weak.
So then it'll be good to have some sort of counter-example and then see.
It would be good, and I would love to. I mean, that's the kind of thing I would love to do now.
So let me just interpolate a comment. So one of the confusions that I get constantly when I read this material is that I'm willing to buy that a wormhole represents entanglement. That I'm absolutely happy with. That's just a linear basis change on a Hilbert space. But somehow that wormhole picture morphs into a bilocal Hamiltonian interaction that gets information out. And I remember we put one on the spot about 2 or 3 years ago. It's on video somewhere on one of our websites, on one of these predecessor meetings. And finally he did say that it has to be non-local in his version of this information paradox. But there's a morph that happens between wormholes representing entanglement and wormholes representing information transfer. And that's the thing I've never understood in this game.
Okay, very
Sorry,
good.
can I just clarify? These are two different concepts of wormholes. One is a spatial wormhole, one is a space-time wormhole.
Yes, absolutely.
So I think we should
Euclidean wormholes
yes.
presumably represent entanglement, but that's why I keep asking, what happens when you go back to the Lorentzian regime? What's the mechanism by which it transmits information?
Okay, no, that was excellent, because certainly it tells us where to aim for, and I certainly want to follow this up with you later on and learn more about it. Let me just switch gears to something a little different. Bit models. Yeah.
Just a very general question that imagine okay. So we are trying to make connection between what we see in the Euclidean picture and the Lorentzian picture, right? But let's suppose that we accept that there is no horizon of the black hole, and you have fastballs. That's the Lorentzian picture. Okay. Then do we still believe that the black hole entropy is given by area over 4 times the Newton's constant?
Yeah, of course. Yeah.
Why?
Oh, so there are some papers I wrote about it actually. So certainly there's no contradiction with that, because let me just say that first. You have some nonlinear solutions. You put them in a thermal loop of beta, the way everybody does, and that thermal path integral can have a saddle point, and the saddle point can be still the cigar. That's not a contradiction with anything. And so you can still have the Euclidean black hole, but its analytic continuation, which is the Lorentzian black hole with horizon and so on, that doesn't have to have any meaning. Just like when you do a saddle point path integral, the actual integral on the real line doesn't have anything to do with the saddle point. So there's no contradiction there. You would simply take all the states you have as fuzzballs, and when you do a one-loop path integral, you look for the saddle point. Saddle point is something which you can then explore in the cross-channel, and I can show you the argument we use as to what you would do.
How do you convert the Euclidean picture to Lorentzian picture? How do you know that particular saddle point corresponds to all the fastballs in the Lorentzian picture? I mean, is there a translation of what the Euclidean picture gives to what the Lorentzian picture gives?
No, so I was just showing you how they are. So we have a couple of results in case this helps you. I'll first try to see if I can just show you how I think about getting the Gibbons-Hawking saddle. So I had some slides on that, so let me see if I can get those. And that's going to be relevant to the discussion later, so maybe it's good to just get that down. Yes, people often ask how you get the Gibbons-Hawking thing to work out in general. So the claim would be something like this. You just start with Gibbons-Hawking, so you're trying to just compute the partition function of something. It's the definition. It's approximate number of states times this. And so you can get out of this is the standard thing, right? Yeah. So the question is, where does Gibbons-Hawking come from? And so for any system, the one loop path integral you can compute, all the states are on this axis, and the beta circle is over there. You have to start with something that works for every case. So you agree that works for every case. With the fuzzballs, you just have some geometry which have some the state is complicated here, but they're all pretty much the same here, but it's exactly a normal system, just normal quantum mechanics. So that's okay, right? Just the states are more structured here than there, but that doesn't matter. Okay. So let's just focus on the RT part of it. I'm going to be approximate from now on. So that's the two-dimensional theory, the R tau space. Tau is in that direction, R is the radial direction. And compute the same path integral in the cross channel. Okay. Now, if this direction was long, and I have to come back in a minute and tell you why it's long. If it was long, and I think in rough CFT language, which is rough because this is not a CFT, but if I just look at RT surface, if this was long, then in this cross channel only the identity will propagate. Okay. So let me go back and say, why is it long? It's long because whenever the GTT is going to 0, then if you just conformally rescale this, it just becomes a long cylinder. Okay. So this is applicable to anything where GT tau tau is becoming small. All this is still true. Just logical steps. If I restrict to the piece where only the identity is going across, that's the answer. I can produce the identity by a path integral over a disk. I glue that in. That gives me the answer. Okay. So sometimes people say that Gibbons-Hawking was a new topology in string theory. I could put any new gravity. I could put any new topology anytime because this was a new topology. It's not a new topology. It all has a logical derivation, and it does have corrections because the cylinder is not infinitely long. The structure wasn't exactly, redshift wasn't going to infinity. It goes up to the Planck length and then stops. There'll be other states psi a also contributing to this, which you can make by other corresponding caps. And so you have to add these things, which I think are a little bit like the subleading caps that Samir Murthy has been finding in his recent work over there. But with that, it's all pure logic. It's a derivation. It's not like you can at least see what you would do and why you get the Gibbons-Hawking. The only thing is you have to say, why did you get a by 4? So if you do this, of course, you'll get a by 4. There's another paper we wrote just last year which showed that if any object is sufficiently close to R equals 2m, what ECO, any extremely compact object close enough to R equals 2m with an extra correction at most of root m, it has to have the same temperature and entropy as the black hole. But that's a different thing. But
I think at the same level, I mean, isn't it true that at the same level, the space-time wormholes, I mean, solving the giving the page curve, right, is also valid?
That's what I would love to see, and I couldn't make it work. Okay, so if somebody can make it work for me at this level,
purely Euclidean calculation. Space-time wormhole is also purely Euclidean calculation.
Absolutely, right? That's exactly what I want. The reason I made this slide is that if I can understand the space-time wormhole or the replica wormhole in language like this, I'm done. That's all I'm asking for. See, this is so. One shouldn't just say, oh, in gravity I can just cap it off. I have a new topology. I just cap it off, so I can do whatever I want. I can join anything to anything. No, this was the logic as to why I put that cap. Because the identity propagated, that's because of high redshift. So it's a long cylinder, so I can only put the identity. I made an identity by a disk, I cap. Just give me any reason like that for the replica wormhole. That's all we are looking for. That is exactly the question. I try to do it for the replica, and I'll show you why I get confused. Okay? I did try to do exactly this, and I couldn't do it. That's exactly why we are here.
Okay. So I think there are two ingredients. One ingredient you need is that if there's some sort of fuzzball scenario, that you need the generic fuzzball to look like the black hole until very close to the horizon. And then you have a geometry which has an approximate killing isometry, which is a boost symmetry near the horizon. Wick rotates to standard rotational isometry. And so everything about the geometry looks exactly like the Euclidean black hole until you get very close to the horizon. And then the question is, okay, there's a little disk that you cut out of the cap because the thing isn't exactly the vacuum black hole geometry close enough to the horizon. But the thing you do in effective field theory, as Samir was saying, is you just glue in some smooth geometry, and that's the Euclidean black hole. Okay, so on the other hand, you're trying to generate this by some standard Hilbert space trace over some complicated states. And so the other ingredient I think you need is that you actually have enumerated e to the a over 4 states. Okay, and that's the thing that's so far missing from the fuzzball program, is that so far the explicit constructions of microstates are incomplete. And so until one has exhibited the full e to the a over 4 states and have them look approximately like the black hole solution until very close to the horizon, then one can question the validity of the fuzzball paradigm.
Absolutely, yeah. So, but one thing I would say to that, I don't think one would ever end up making all the states of a black hole just like one had never made all the states of a planet, right? And that somehow looks to me the wrong way of going around the question, but going closer to what Ashok was asking. If you have anything which is at a given temperature, why you should add a cap to it? We just saw the reason. So if you have high redshift, only the vacuum contributes. That's what we just showed, right? If it's a high redshift, it's a long cylinder, it's a vacuum, you cap it. That answer gives you a/4. So it actually tells you if the redshift is high, and you can always ask, why should the fuzzballs have high redshift? That's not been answered. But if they are high redshift, if they are sufficiently compact, they have to have this entropy. That's what was being shown here.
Well, but you're postulating that there's some structure at the horizon, and everything we know about so far collapses into a singularity. So there's still a gap in the logic.
No, they don't collapse, right?
You know, Joseph gave us a talk about, you know, what some possibilities are for generating structure at horizon scales, and that's basically what this whole program has been about for the last however many years. But I think there's still missing ingredients as to explain, you know, how it is that all this thing that you're building out of essentially supergravity doesn't obey the usual Penrose type.
3+1 dimensional physics, no.
Well,
There's
still a Raychaud-Hurry theorem. There's still a focusing theorem.
Yeah.
Right? There's still apparent horizons.
Should we just move on to the next section now? I'm just wondering. Shall I move on to the next one?
20 minutes, so we should probably move on to the
Next part.
unless there are other burning questions.
But yeah, everything you said is, I agree with 100%. Yeah, we should definitely find
we all
more.
know the strengths and weaknesses, and some, well, not all of us, but we know the strengths and weaknesses of the current microstate geometry fuzzball program. But the purpose of this session is to sort of take a more jaundiced look at the other solutions that have been fated to this problem that we've been told that, you know, this has solved the problem and microstate geometries are no longer needed.
So, okay, so let me bring to you my other set of confusions. So people have been writing lots of papers playing with bit models, and those papers are a little hard to read because once you start making bit models, you get very enthusiastic and carried away. I know it happens to me because you keep writing lots of things and the papers become very complicated looking. But let's just stand back and see what could these papers possibly be saying. Okay. So just to remind you what we know about bit models, there was the bit model, it starts with Hawking, right? The two entangled pairs, you can write it like this. So you just have one bit here, and you can think of them as spins or whatever, so you can write them as 0, 0, plus 1, 1. And then you can make a model for burning coal, where you can make this as 0, 0, plus 1, 1, and then this guy comes out. So now they're entangled as 0, 0, plus 1, 1, but they're not entangled with this. So you can make bit models for coal, and you can make bit models for black holes. The only difference is in the black hole case, the entanglement keeps increasing between what's inside and what's outside, And in the coal, since these guys also come out, it's mostly between outside to outside and not with what's left behind. Just repeating the obvious. So if you keep making bit models, what can you possibly get out of it? So that's the question. All the bit models you see in various papers, what are they telling us different from this old story? Like if the Hawking is inside and outside, coming out of the vacuum, and a coal is, well, you know what a coal is. You can make lots of models of coal. Does somebody have maybe one line or one paragraph summary of what we have learned from bit models? You don't want my answer, so I just want your answer.
I think it's a bit like in the original paper of the page curve. I mean, he didn't have a black hole, but he told us what we should be aiming for.
You mean Page's paper? No.
Yeah, the page paper on the page curve.
Oh, by Don Page.
Don Page.
Yeah.
Yes. That was a paper that didn't have black holes anywhere, but it told you what you had to aim for.
Absolutely, that was the coal.
And I think that this is what the bit models are doing.
Very good. That was exactly my question. Page told us what coal does.
Yes.
Right. And the whole problem is that black holes don't do what Page wants them to do. Right?
Yeah.
Good. So this we know. Yeah. What's there to write after Page? Why are there 100 papers on bit models? I'm just trying to ask a very rude question.
I mean, it's like the Preskill-Hayden mechanism. That's, again, a bit model.
Very good.
Yeah. I mean,
I'm going to agree with you.
I mean, it's telling you about, well, if you want a black hole to be a unitary system, it should be doing.
So I agree with you 100%, because this was my second point here. The papers on bit models like those of, I'm actually getting the pointer, of Preskill, Swingle, and so on, many people have written these papers. Are they just talking about properties of radiation from coal? Because when I read these papers, again, they're also very long, so I don't know how many people have read them. Section 1 talks about the black hole. It mentions the word black hole. At section 2 onwards, they start with a bunch of bits which are just unitary. Some are coming out, but they're just bits coming out. They're not actually ever coming out as 0, 0, plus 1, 1 out of the vacuum. They're just the bits you start with, and they are being reshuffled. And you can entangle them in various ways. So in fact, are we just learning more and more properties about radiation from coal? So Brian Swingle came and gave a colloquium at OSU, and I talked to him a bit after that over Zoom. And actually I asked him, are you extracting more and more properties of coal? And in the end, he said, yes. We are learning more and more about burning coal. So what can you learn about burning coal? If something is pretty random, at leading order, you get the Page curve. You can compute subleading corrections. You can throw more things into coal. It will reshuffle and come out. You can see after how much time something comes out. You can do subleading corrections exactly as you said to that. That's the Hayden Preskill thing. But it's very confusing to me because they all begin with saying we are talking about black holes, which would be this. And that's the one which has the problem. But right in section 2, they all switch to coal, which has no problem. I want to know if this understanding of mine is correct. This is what I learned by looking at whatever papers I could read. I may be completely wrong, and I'm just trying to see if I can extract something about bit models, about information puzzle, which I have missed from all these papers. I shook hands.
Well, I mean, to me, but just, I mean, it's, if you can find some mechanism using gravity where you can reproduce some aspect
of coal,
like, well, people have done with the Page curve, then that's good. That means that.
Then black holes will also have that.
It's not that you're
problem.
solving all of the problems, but you're solving, I mean, you're.
Yeah. So you can show, if black holes are shown to be coal by some other mechanism, maybe like fuzzballs, then you can learn something about black holes because you already knew about coal. Okay, that's good. Let's see if that's what Ashok was saying.
Yeah, I think one of the ingredients, sorry. It's okay. One of the extra ingredients that put in these bit models is the fast scrambling, right?
Yes.
That which is not generally a property of the coal, but it's supposed to be a property of the black hole, right? And they use it for deriving various properties of the evaporation from these bit models.
That's why I have a slide for you. I knew you would ask that. I knew somebody would ask that, so I have a slide for you. Okay. Yes, that's exactly the question. I'm glad you asked that, because if I give you a lot of bits, and I play with this bit going here, this bit going here, you can have a lot of fun with that. On the other hand, where have you put in some property of the black hole? That's what we should ask, right? Why is it different from a piece of coal? If you can identify even one property, that would be good. So sometimes people say, oh, a black hole has lots of states. And that's not true. Okay, that's not what Ashok is saying. I'm just saying sometimes people say that because if you take a 10 to the 10 Planck mass black hole, it has 10 to the 20 bits, right? M square, 10 to the 20 bits. A piece of coal has 10 to the 23 bits. Okay, so it's not a question of number, right? There's more bits. But then, so what is the problem? If you just have bits, you're not putting in any dynamics between them. There's no quantum gravity or something, just playing with bits. But you could be talking about fast scrambling, but now fast compared to what? Because, but there's a dynamical way to talk about fast scrambling. If you have 100 bits here, suppose one bit goes out, there's no time in the bit model. You take them out one by one, just a time step. But you could ask the following question. After this bit is gone, the remaining 99, do they have time to talk to each other to get to a generic state before the next one is pulled out? That's the only parameter you can put in bit models. Good. So I have a bit model for you, which doesn't have a black hole, which has exactly that property of fast scrambling. You take a box of gas with 100 atoms, and you make a very small hole in it. Each atom has a spin up and down, whatever. And so once in a while, once every 100 years, this guy leaks out, and that's the emission from the black hole, or whatever. But if I make this hole small compared to the box, you can see that these 99 guys will interact with each other as many times as you want before the next guy comes out. You can make as fast a scrambler as you want. My claim would be that by taking atoms of, let's say, spin half in a box, I can reproduce every property of a bit model that you could ever hope to get from a black hole. So anything anybody can derive from a black hole is from a piece of gas. I would love to hear a counter to this.
Yeah, so I think that they will probably say that that's the model of the black hole. That if you have a fast scrambling, that will be the model for a black hole. Right?
So,
I think
so he's saying this is also a model for a black hole.
Yeah.
Yeah, he's agreeing this is a model for a black
because
hole.
they are trying just using the beat model with fast scrambling as a model for the black hole, right?
That's fine. Good. So let me see if I can summarize what you just said. I'll just summarize that from my understanding that I'll send to you. It's not that you can hope to learn anything about the information paradox from any of these things, because you already assumed it's like a box of gas, and a box of gas has all the properties that you're ever putting into the bit model. You can't get out more than you put in. And so all you're saying is that if you can ever make the black hole be like a piece of coal, which you will need fuzzballs or something else to do, once it becomes a piece of coal, you're hoping it's a fast scrambling piece of coal, or let's say it become like this box of gas, and then you can use this box of gas in your lab and study all the properties for black hole without ever having to make a black hole, because I do have this box of gas at home.
Yeah, I think that's my understanding is that the beat models are not supposed to solve the information puzzle because it's already built in, right? It's a purely quantum mechanical.
That's all I wanted to say. It's already built in,
Yeah.
and there's nothing you can
So
build.
they are just studying some properties of the black hole using the fast scrambling property. I think that's my understanding.
It's a little misleading to call it properties of a black hole, because all those papers, wouldn't you say, could equally well be titled, we are studying properties of a box of gas with a tiny hole.
With
If I change the title, will it be
fast
okay?
scrambling, fast scrambling
Yeah.
box.
So I just want to change all the titles of those papers to, okay.
Yeah.
There was a question there.
Okay, thank you. So, at first I had a question about the box, but before that, maybe the point is that in papers, about like quantum mechanical toy models of black holes, the point is that, like, it's true that information is kind of already, like, the system is unitary by construction, but the point is you're trying to study unitary evolution in some, fast scrambling, chaotic, large N, many body quantum system.
Yeah.
Okay.
I agree, yes.
So
if you do that, yes.
Yeah. Then I don't understand very well, like, what's the definition of this box with a small hole? Because if there is a gas inside, you have to make the gas interacting, first of all.
Yes, it is supposed to be.
Okay. Then it should be a quantum many-body gas. It should not be a classical gas of particles.
No, even classic. Oh, yeah, because of entanglement. Yeah, it's a quantum
Because of
gas.
entanglement,
Yeah.
and also because of scrambling. Like, scrambling is not, we're not talking about the classical Lyapunov exponent. The scrambling is a property about
Entanglement.
And the distribution of entanglement in your system.
Absolutely.
And then if you suppose that you have that gas in the box, then you put something, then your system is no longer a closed quantum system. So I don't know, it doesn't seem to me like this is a good model for unitary black hole evolution, because as soon as you put that, you have a dissipative term, and you have like open quantum dynamics, right? Like you're explicitly breaking unitarity if you allow particles to get outside of that box, right?
So wait, let me just see if I understand your question. I thought this was okay because I was modeling a black hole which is emitting radiation. So this was like the radiation which is going away. And I did say there was spin half object, so spin half quantum is a quantum. They entangle and this flip their spins and entangle with each other and everything. So I have spin half atoms which are bouncing and interacting, and this guy going out. My system will always include everything, so it's unitary. This part, of course, is losing atoms, but that's the same for a black hole. Some part is going away from the black hole. I have to include both the radiation and the black hole to make it unitary.
Okay. So
and
it's
I'm
not
doing
open.
that both
There's
times.
something closed on the other side. There's another box on the other side, basically.
Absolutely. So even in Hawking radiation, I would like to collect that radiation. Otherwise, I can't make the questions about anything.
Yeah, I was confused by the open box.
Good. So it's open only in the sense this is the radiation from the black hole. This is the black hole. All the atoms collecting here are the radiation zone, and then it exactly maps to the black hole problem. That was the point.
We have about 10 minutes before.
Okay. Okay, if we just have 10 minutes, maybe I'll just tell you the last part of the story. I don't have a question for you here. I only have my confusions. But if you are willing to hear the story, let me give it to you, because then hopefully somebody can help me. I worked for a long time in trying to understand the derivation of the page curve. So you can see that's the most exciting to me because page curve comes down, it's so nice. Okay, I didn't succeed. And for me, success means that I can go to the board from the beginning and derive it completely in front of an undergraduate class, because those guys don't forget anything. And they don't forgive anything. Okay. So let's just start. I know what is Rényi entropy. It's defined as trace of rho to the n, and we all know if we take limits of that for n going to 1, we get the entanglement entropy. So we would love to compute Rényi entropies. So let's compute a second Rényi entropy. That's the simplest thing you can do. And so this is what I picked up from various papers. I'll just try to tell you the story, and you can see how badly I am confused. So this part is supposed to be the outside radiation, this flat space, and you can see the radiation quanta over here. And the inside part I can either represent by gravity or by the boundary CFT. You can see this lines like the boundary CFT. At some places I'll replace it by gravity. I'll keep doing both. Okay. So anyway, let's first talk in terms of the boundary CFT and the radiation. So this guy has some excitation which you could think of as a black hole. It emits stuff, and so this guy gets entangled with this, and the total state can be called psi. That look okay for notation? So what do you make? How do you make a density matrix for these guys outside? You take this psi here, which I've drawn on this line. You take another copy which has the dual, so I've written it psi as the bra. And then if you trace out this part of the state, what 2 degrees of freedom were here. So there were degrees of freedom here which I haven't drawn. They are just entangled with these guys. So if you trace these guys out, you get a density matrix which you call rho of the radiation, and that's over here. Just standard notation. Nobody complaining? Okay. Then how do you compute trace rho square? You make 2 copies of this. One bra and one ket makes a copy of rho r. Another bra, another ket makes a copy of rho r. The states which you get here, you can call them I, j, k, and l. But then you have to trace them because you want to compute rho r square. So if you identify this one with this one, then it multiplies this matrix by this matrix multiplication. And then if you identify this one back with this, you get the trace. So hopefully that is clear. That's trace rho square. Okay. Now my confusion starts. If you believe in ADS CFT in its original plain pristine form, which I do, then every state in the CFT is dual to some state in the gravity. So now you see I have not drawn any gravity here, not any CFT here. There's just some messy gravity stuff. But every state here was some complicated state here. No EFT, nothing, just something here. And then I do this, and so the definition of trace rho square is the same. You trace this state with this state with this state, same thing outside, and this is the Rényi entropy. But this is exact. I just want to be everything exact. I get very worried when people jump to approximations too early because I don't understand the approximations. Okay, let me go on. Now the replica wormhole people come and they tell me, from what I understand, and I can be wrong on anything I say from here onwards, they want to add another term where instead of this being traced to this and this being traced to this, they would also like this guy to be joined to this and this to this, a different way of tracing. And if you do that and look a little carefully at where the arrows are going, this will give you a trace of rho r whole square. And so they would, if you just follow the maths of what they are doing, forgetting the physical arguments, the correct Rényi entropy, which I would call correct, it was just trace rho square. But if you add the extra term with some coefficient which they'll take to be exponentially small, you add to it trace of rho whole square. I don't understand that term, but I'm just first telling you mathematically what happens so that everybody is on board. Then you might think, see, if alpha is small, this should hardly make any difference, except for the fact that when the row matrix is big, trace of rho square is much smaller than trace of rho whole square. And so that's why the second term can start competing. And what do they actually, you can just see that very easily. If you take a density matrix, which is very simple, it has just got all 1 by n's, and n cross n matrix will look like that because trace has to be 1. Then trace of rho r is 1, but trace of rho r square is 1 over n. So you can see that if you take trace of rho r square, if you add to it even a little bit of trace of rho r whole square, it can make a huge difference when n is big. Okay, so then they find that if you add this extra piece, when n became big, normally trace of rho r square becomes very small, but this guy stabilizes it. It can never become too small because this is always alpha, because trace of rho is 1. Why is that important? If you just go back to the definition of Renyi entropy, you take the trace rho square, you divide by something, but then you take a log and a minus sign. So if this guy becomes very small, that's when Renyi entropy is very big. Okay? So a signal for big entanglement is a very small trace, you can see from here. And so if you can prevent the trace from becoming very small, then the entanglement can never become very big. So that way you can prove you can never entangle too much with the black hole, and so you can't have like an infinite number of states inside, so you've learned something. Okay. But all this happened because you replaced the trace rho square by trace rho square plus a little bit of trace of rho r whole square, and I keep trying to understand why, and I haven't succeeded. Okay. So let me see what happened, what I tried to get there. This just tells you what they are doing mathematically. If you take all the complicated paper and reduce down to the essential math, it is this. So all these people are very polite and they helped me a lot through emails. I got even more confused, so that's what I'm going to tell you. So first thing I said was the wormhole contribution looks incorrect. I know what Renyi entropy is, who to join to who. If you join somebody else to somebody else, it's not Renyi entropy. Why are you doing this? I got different answers from different people. So Marov has this theory that gravity is actually non-local with wormholes that connect across arbitrary log distances. Goes back to the old Coleman et al. Theory of wormholes. And then there's a non-local correlations in the theory, not acausal but non-local. And then if you remove them, you can integrate out those wormholes, and then you get an ensemble average theory, and that in fact is what is somehow leading to this kind of wormhole. Okay. So there was a question already for me from the back? No. No, I think it's okay. So then I went and asked the other people, do you think that string theory is ensemble average? Is that what you're doing? And they said no. String theory for which we want to apply it is not ensemble averaged. The reason we are putting the other term is different. And let me see if I can work the pointer. So the pointer doesn't always work. I'll just read off from here. The answer which I got from Maxfield, I put question marks on these answers because I could be interpreting what they said incorrectly. But in the end, I did ask Marov if he's saying the same thing as this, and he said no. Okay. So the exact string theory does not have any such wormhole term, which is what I would also believe. There's no, this is exact as exact. Why would there be another term? But when we take the low energy limit of the exact theory, we get a non-local effect between systems which have arbitrary large separation. Okay. So I was very puzzled. If I take a low energy EFT limit of two things which are very far away, how do I get a connection between them in the low energy EFT? So I asked them if this happens for an ordinary field theory, because if I just go from QCD to mesons, I can do it here. That's what a low energy EFT is for me. And then on Mars, I have QCD going down to mesons. That's a low energy EFT. I have taken low energy EFTs before many times, but it's never given me an interaction across arbitrary large distances. And so Maxfield told me that's because gravity is a special theory and this can happen. Okay. I actually don't think gravity is a special theory. For me, everything I've learned from string theory, it just looks like a more complicated field theory to me. Okay. So I don't understand this. So the two answers I got on where the non-local term is coming from, at least these two answers didn't quite fit for me. And what was worse was, I then said, okay, I will give you a counterexample and then tell me what happens. So what was the counterexample? I said, let's just take 2D gravity, which we can quantize exactly. It goes back to a CGHS model. I'm so old that I remember the CGHS model, but some of you might have read about it, though you probably weren't born then. So in the CGHS model, you take 2D quantum gravity plus scalar fields, and you can exactly integrate it. So I asked people this question. You can even put it on a computer, because people do 2D gravity with dynamical triangulations. You guys heard about dynamical triangulations in various contexts? People have actually been putting it on the computer. So I asked the following. You guys use 2D gravity for so many things. At least tell me the following. Suppose you take 2D gravity plus scalar fields, put it on a computer and just shove it in there, and you make a black hole by sending a shock wave with one of these fields and do everything like CGHS did. Will the page curve go up or come down? Actually, that's a clean question. You can even compute in the computer, right? I want to get a vote in this room before I tell you what people said. If I just actually take 2D quantum gravity, you can do it analytically by CGHS or dynamical triangulation or anything, numerically, and just put it in the computer and compute the page curve, you can see everything coming out, right? You can compute the entanglement, just quanta. Full quantum gravity is here. Will the page curve go up or come down? How many guys say it will come down?
I think if you have to say a little bit more what your rules in 2 are.
I will. Good question, and absolutely, you have to say that. Good. So the one thing which was mentioned, I'm glad you brought that up. People said in the CGHS model, if people remember, the page curve kept going up. Okay, everyone knows that. But I said, oh, now if we apply the rules that we now have, this one with the extra term in it, and people wrote a paper. There was a paper of 3 authors. I think I have it on the next slide. The page curve comes down, because if you use these rules, the page curve always comes down. We just talked about it. Why? So if you ask them what is different, the answer you get is CGHS did not allow topology change. Okay? So let's put in topology change. Well, it's a 1+1 model, so topology can do very little. You have a one-dimensional line. It can break the line. You have to have an amplitude for that. And you can rejoin the line. You can break into 3 segments, 4 segments, and so all those processes are there. Good. So now we have a more refined question. Take links, and then did I write it down here? Yeah, here's the model. So you take this space-like slice. In the black hole region where you want strong gravity, let's allow that this link can break into pieces. They can rejoin. They can do all kinds of things, and then put the whole thing in the computer. They can join. They can break. We'll make a rule for that. Now tell me, if with this, you put this in the computer, will the page curve come down? Is there anybody who says that with this it will come down? Is there anybody who's willing to say it will go up?
Yeah.
Don't put him on the spot. He doesn't have to answer. Nobody has to answer.
I'm just trying to.
Pardon?
Now you're allowing what change? You're allowing the.
So you're allowing the space-like slice to break, right? I mean, because you have to allow topology change. The only way you can change topology, this is all a Lorentzian theory, right? In the Lorentzian theory, you can break things, align, and you can rejoin them. That's the only topology change you can have in a 1+1 gravity.
You're still doing a Lorentzian calculation with.
Everything Lorentzian. I'm going to put in the computer. CGHS was Lorentzian.
Okay.
Okay.
So it's nothing to do with the recent calculations.
So actually, people wrote a paper on this CGHS model, used this replica wormhole or rules or whatever, the QES rules, and argued the page curve comes down.
But those are Euclidean.
The rules are Euclidean, absolutely. The rules are Euclidean, yeah. But the question is, if they are giving those rules, I'm questioning the rules because I want to know if I apply those rules. Suppose I take that paper seriously, let's believe that paper. Then those rules tell me that in this case, the page curve comes down.
No.
With topology change.
I don't think so, because the rules, you're applying those rules to the Lorentzian theory.
They're also not the same rules. This is not the same topology change that they were discussing.
Good. No, I understand. But those Euclidean rules, there's no Hawking evaporation in a Euclidean theory. Those Euclidean rules, whatever the rules are, you're welcome to use them. In the end, they are telling me the page curve comes down in the Lorentzian theory. Yes. There's no page curve in the Euclidean theory. And so I'm asking, take the Lorentzian theory of 1+1 dimensions. Yes. You can make the analog of the rules here, but there are no rules possible except breaking and joining the line, and you can put whatever amplitude you want for them.
This may not. Okay, my guess is I haven't done this calculation.
Yes.
But I don't think this will be the same as applying. Meaning, my guess, I'm going on a limb here, would be that it does not come down.
Good, because we wrote a paper showing.
Or it could, it may or it may not, but there's nothing obvious that follows from the fact that in the Euclidean calculation it comes.
Good, that's exactly what I want to talk to you about. That's exactly the point that I'm worried about. We actually give an argument in this paper, which you can go and read, that the page curve will keep going up, which is exactly what you said.
But I don't see a contradiction between those.
So hold on, I do. So I just want to ask you that. These people said that CJ's model with those Euclidean rules has a page curve coming down. I'm just worried that I don't know what it means. Because the page curve is in a Lorentzian theory. They are saying we are using Euclidean rules, whatever the rules are, to predict that the page curve in some Lorentzian theory comes down. I'm just going and asking, let's try to see what they do. What Lorentzian theory could it be in 1+1 dimensions where the page curve comes down? Let's think about it for a second.
The page curve is computed by saddle point. You could have Euclidean saddles that contribute to Lorentzian correlation functions, Lorentzian quantities all the time.
All the time, absolutely.
So I still don't see the issue.
The issue is that now you have to now say there's a calculation which shows that the page curve comes down by using Euclidean rules. I don't trust the rules, so I have to do something explicit. I can ask you the following question. Show me which Lorentzian theory these rules could possibly mean anything for. And when I go back to 2D, there are very few choices. And I don't have to make the choices, I'll let you make them.
But sorry, can't you even say, show me a Lorentzian theory with some rules? Because you don't even, why are you assuming it's the same rules applied to the Lorentzian theory?
No,
right?
it's not the same rules.
Yeah,
I'm not saying that.
Yeah, exactly.
Show me any Lorentzian theory with any set of rules in which the page curve comes down. And if you do this to that,
I don't
then
think anyone knows this, right?
good. But I'm going to argue that any Lorentzian theory, well, the argument here was any Lorentzian theory that my argument would be the page curve will always go up with any rules. Okay, so let's talk about that. By any rules, I mean any rules which don't have non-locality between, if any rules which don't have non-locality between the black hole and outside, this argument here, I can concretize it more if you want. We just gave an argument here. Anything which doesn't have non-local effect from here to there, the page curve will keep going up. That's what that one shows, any theory. And now I'm questioning whatever rules people have cooked up for the Euclidean theory, I'm just asking you, what do they mean? Because you have to put this together with that and then tell me what they mean, right? So that's that's my sad story on this, because, okay, there's just one more part. Maybe I'll just tell you this part also, and then I'll stop. There was a very nice paper which I spent quite some time reading by Liu and Vardhan, and there were a couple of follow-ups, which at first looked very promising. I just loved this stuff. They start with some work which was done by the StatMech people, where you take an entangled state between two systems, one with states labeled I, one with states labeled A, with arbitrary coefficients. It's normalized. And it's a random system, like the StatMech people have. So the average coefficients, you can put the average to 0, but then they have some kind of a dispersion, the entanglement, right? So you can do that. Then you can try to compute the running entropy, but because this is StatMech, I can now do these various averages. And if you do these averages, you find there are two kinds of terms. This C can contract with this C star, or this C can contract with this C star. I think I've drawn it wrong. This should go here, and this should go here. Anyway, there are two ways to contract C's with C stars. And that looks very much like two pieces, like the normal contraction and the replica contraction. The whole lesson is you shouldn't run away with things too quickly. Just because things look like things doesn't mean they are things. If you look very carefully at what the contractions are, if you go back to the StatMech papers, what they are is the following. You have a system A and a system B. In one set you contract, if you are to apply those rules on the previous page to thermal systems, in one case you're doing Z square for system A and Z of 2 beta, Z of beta square here and Z of 2 beta here. The other set of rules give you this one. And why did the StatMech people do all this work? They wanted to prove that if you have two ordinary systems, A and B, and you entangle them maximally like thermal, then the entanglement is given by the smaller system. That's obvious, right? You can, if the small system is 10 bits, this is 20 bits, entanglement can be at most 10 units, can't be 20. So they know that when they change the size of the systems, this thing has to go from this one dominating to this one dominating. And so you find the total answer, if you do the saddle points, is given by this plus this, and then you find if this system is bigger, this piece dominates, this piece of the system is bigger, this piece dominates. And so there's nothing to hide here. It's all very clear. And if one of these was the normal contraction, the other was the replica wormhole, I would be so delighted. I have understood everything. Except this was section 2 of the paper. And you go to section 3, and you find that the contraction they do for the gravity case, as far as I could make out, are not the same. So this time, one is the usual one we expect. The replica wormhole, from what I could make out, had this contraction. You remember we said trace rho square? So this is just a separate trace rho. You can join them, there are two systems, you can join them by line flag. This is a rho, trace of rho whole square. So the two things didn't match on. So what is happening for me is that I'm trying to dig into these papers all the way to the last to see if I can understand where the second piece comes from. And I'm not saying it doesn't come. It's just that I keep following it down every paper to the end, and I've got great help from my students and postdocs and everybody, and from the authors. And I still don't have anything which I can present to anybody that I understand something. So that's what happened here. And the one we just talked about section before, this I would really like people to give me an answer for if they can. There is a Euclidean answer which gives for 2D gravity that the page curve comes down. I think this is the place I would love to see it pinned. It has to correspond to some Lorentzian model in which it comes down, these rules. What do these rules mean? Because I can show explicitly here, I can argue to you pretty strongly that if I only mess up the gravity region in some way without any long distance corrections, that is if I don't have long distance corrections from here to here, the page curve will keep going up. So this is such a clean system. You can make any Lorentzian rules you like, put them in the machine, and the page curve will never come down unless you have these non-local things. So maybe this will tell us really what's going on. You had a hand up. Yes, John. Okay, this is all I really had to tell you. So anybody who has anything useful to tell us at this point would be very nice. Cube is there.
Any questions or comments?
Here.
So do you claim that you have something like a theorem that at least in the CGHS model, if you don't introduce some non-locality, then there's no way to have the page curve going down? And then, I mean, can you specify what kind of non-locality is necessary in order to have this? Because, I mean, having a model like that, I think it would be extremely useful. I mean, you're saying that you can have, I mean, Lorentzian model, you have a Lorentzian model of evaporation, and then you can pin down precisely what's needed in a Lorentzian model.
Yeah, so pin down is a strong word because, as we just agreed, you could make any model, right? So it's very difficult to prove with any model.
Wow.
But yes, I'll tell you what these rules are to get to this conclusion we had up there. So firstly, if you want to make a bit model which does have non-locality and get some entanglement out, we gave a bit model for that. Okay, so that's separate. That's nothing to do with CGH. You can all make a bit model where you have non-local Hamiltonians and you can get the page curve to come down. We have a bit model which can show that. But I don't believe it, right? So that's different. Now, in this, the argument is very simple. If you want to keep a smooth horizon, what that means is that you can't have this breaking and joining happening all the time. You can break it once in a while, but you can't break it all the time because otherwise it's just joining and breaking all the time. So it can stay there, and once out of every 100 steps you can break it. Inside you can break it as many times as you want. Okay? The way the Hawking calculation goes and the way the small correction theorem works, so you're going to worry about small corrections all the time, right? Because you can put small little entanglement and the page curve shouldn't be affected over all these million quanta. So use the small correction theorem a lot. But the point is, if only this part is basically behaves sensibly except maybe 1% of the time, okay, that 1% is a small epsilon, you'll always create a new pair here, which is entangled. What you do to the pairs after that, it doesn't matter at all, as long as the structure is unitary. So that's important in the small correction theorem. Once the pair is produced, what happens to it inside, how it's ground up, is not matter at all. So all this breaking up here doesn't change anything. If you break this more than 1% of the time, you don't have some smooth thing at the horizon. Just stare at this and you will get the proof yourself. How on earth are you going to do that? So it just keeps going up. And any delicate correlations introduced can't help you with as a small correction theorem. It's that simple.
I think that what you're telling us is that the Lorentzian continuation of the Euclidean calculations is not any of these models.
Yes, it's not any of these models. Yeah. So now tell me, what is it? If you have a smooth horizon and if you have no non-local terms, I can't do anything. But if you can do it, it's great.
Maybe since you asked for a rule, here's a possible rule.
Good.
Don't allow for topology change, but allow for non-trivial inner products between different slices. So a slice, let's say you have different geodesic slices. Allow for inner products that are given by a random matrix.
So will the inner product change from slice to slice? Because that's not a unitary process. So
no, I'm saying that the set of states that naively in the perturbative Hilbert space you think is forms an orthogonal basis of states.
Yeah.
Is not actually an orthogonal basis of states. There's some slight non-perturbative corrections to every inner product that are described by a random matrix. I'm just giving you a rule.
No,
like, you can check it, and I think it will work.
So we checked it because that, I think, is exactly what Maxfield did. Maxwell has this model where the dot product is actually changed by a small amount at every step, except till you get to the end point, which doesn't matter. If you do the Maxwell thing, so we took his thing and we computed the page curve, and we found the page curve is going up. So we wrote to Maxwell and said, your abstract says your page curve will come down, but we've taken a model, we worked out the page curve, and we find it's going up. And he said, of course it's going up. So this is what he told us, and that paper we worked through in great detail, so I'm happy to sit down and show you all the calculations. If you compute the correct Renyi entropy the way I defined it here, with the changing dot product that Maxwell put in, the page curve keeps going up. What's happening in all these cases is, if you compute the wrong Renyi entropy, which means you add the trace rho square term which you're not supposed to add, if you compute the wrong Renyi entropy with these extra random dot products, they're not random, he has a rule for them.
Sorry, I'm suggesting random. If you
Okay,
you
then
have
that's
a
different.
different
So he was
if
trying
you
to-
set the
yeah.
inner product to inner product squared to have a certain average value, it will not work. It depends whether you use the average square versus square of the average, and your
So is that
the
more
way in
like an
which you
ensemble
compute.
average theory then?
Yeah. So
And then
that
you
will
can do
be
lots of
ensemble
things.
average
Okay.
dependent.
So
If
I have not been talking about ensemble average. You can probably do things which are not here. We've already agreed to that. If you do ensemble average, new things can happen, like Marolf was saying. And because string theory is normally not ensemble average, I didn't go there. And it's true, here I was not assuming ensemble average.
Okay, so then my suggestion is just put an inner product that's a random matrix, and I'm not sure that that's exactly what.
Good. So then you would say that the page curve coming down calculation with the replica wormhole represents ensemble average theories.
No, I think the page curve calculation will be true to high accuracy, regardless of your choice of random matrix, because the page curve is a self-averaging quantity, meaning that regardless of
of course.
which random elements the matrix has, the shape of the page curve will roughly look the same.
So I would love to know more about that, but just repeat my statement. In a theory which is not ensemble averaged, or doesn't have any randomness in it, but just has some rules like Maxwell took, the page curve will keep going up. Okay, whatever rules you make. But yes, if you want to play with things like random dot products, I would love to hear. Okay. There's another question. Okay.
Suppose you make a black hole from the zero brains, and this zero brain black hole emits Hawking radiation. I would have expected that in the exact theory there are heavy open strings that connect between the Hawking radiation, the zero brain, and the faraway black hole.
Very heavy open strings.
Very heavy.
Yeah.
And if you were to integrate them out, you would not see them in the low energy effective field theory.
Absolutely
So
true.
could this be a string theoretic realization of this non-locality that you mentioned before? Or
No, it's not, because this effect, if you integrate out those heavy strings, that's where you just end up finding that the effective action of the D0 brain has a velocity to the fourth term, right? That's the effect of those stringy effects. But that effect falls off a distance also, right? So it's a small correction, and the small correction will never fix anything. These were order 1 effects.
We probably need to finish up. Last two questions. Gabriele first.
So before your answer to Luca, you were saying I'm not putting any ensemble averaging, and I agree that I don't think about string theory as an ensemble average. But when you work with some gravitational theory, either this CJHS or anything like that, I don't think it's a choice you're allowed to make. Like the theory is what it is. If you find out that the theory is actually ensemble average, that's what it, you cannot say.
No, I agree, yeah.
So
So
then
now the normal
if the
CJS was not.
CGHS model, if you use that to make a calculation, it's it's an output whether the theory is ensemble average or not. It's not something you choose, right?
Okay, CGHS, they started with a given Lagrangian and action. So that one was not ensemble
but
average.
any theory of gravity, any semi-classical theory
You could
of
have
gravity.
another theory which is ensemble averaged, yeah.
No, I'm not averaging on the gravity side, Also, any, 2D gravity, also JT gravity has a Lagrangian, and you look at it and it's a single Lagrangian, right? There's no averaging parameter in the Lagrangian, and yet the theory is ensemble averaged, right? It's not an input, the ensemble
No,
averaging.
it's supposed to be the
output.
effective field theory of the SYK, which is ensemble average. The JT gravity is not.
As its own thing, I think it's... yeah. It's not. That's only an approximate, I would say, correspondence. As its own gravitational theory, independent of any boundary. Like, you don't get to decide whether gravity is averaged or not. The gravity path integral tells you that.
Okay.
And you have to
So
live
here
with
I've
it.
assumed the gravity path integral CGHS had together with topology change allowed. And that one gives you a rising page curve. That's the argument I'm making. If you do some other Lagrangian with perhaps other averaging properties.
No, there's no average.
Okay,
I'm
good.
not doing any average.
So that path integral, so here the claim was, and I'll be happy to discuss this, outside. If you write the same gravity path integral, which is just used by CGHS plus topology change in exactly this way, the page curve will rise. If you contest that, I can argue more.
No, I'm just, like, in CGHS, there's wormholes, right? And so how do you interpret those, right? Like, the point is the existence of those wormholes, which are there in CGHS, tells you that either your theory must have some kind of average.
Okay, so then you're saying it wouldn't be the simple normal Lagrangian I'm thinking about in CGHS.
No, it is the same. Like, yeah, it's the same Lagrangian. It's just that Lagrangian contains wormholes. Like any, like 3D gravity contains wormholes, JT gravity contains wormholes, even...
Are those on the Euclidean side or the Lorentzian side?
Euclidean, but then you
Good.
can analytically
Euclid, you have them.
those.
You can absolutely do everything you want, but in the end, tell me if you have a Lorentzian Lagrangian which is fully quantized in the computer by discretization with any rules you want, which will give you a falling page curve. You just tell me that is true, and I'll dig into it with you and see what's your model. I'm claiming that no model can do this without the non-local interactions.
All right. I wanted to follow up Luca's suggestion. So if I had an inner product, which was some big term down the diagonal, and then a whole bunch of off-diagonal terms, which are approximately a random matrix, is that something that you would regard to be a large correction because the inner product of the state is roughly coming half from the diagonal terms that you thought were approximately orthogonal, and now, roughly speaking, half of the support of the state is overlapping with things which are completely different?
Okay, so I'll answer it for you in the context of Maxfield's model, which had small changes to the dot product. They may not be random because randomness is an extra thing you can add to it. But when you change the dot product, you can immediately write that as something where the dot product is not changed, but the state changes a little bit from step to step. Right? Because you can always take a basis where the dot product is delta ij. I mean, it looks like changing the dot product, but what he did was he kept the state on the inner slice the same from the state in terms of bits. He kept it the same from slice to next evolved slice, and he said the dot product changes a little bit. Whether it's numbers or random numbers, right now it doesn't matter to me. You can always write that change as if the dot product is always 1, 1, 1. That's just a basis. And the state changes a little bit. So if you had 0, 0 here it could become a little bit of 0, 0 plus 1, 1. Right? So you can absorb that in the change of the state. It makes zero difference if the change is made inside because it has to be unitary. How you reshuffle the guys inside makes zero difference. The change out here is order epsilon to the last bit which you're emitting. The small correction theorem goes through, and so the page curve will keep rising. I don't see anything you can get with the randomness. I haven't understood that because Maxfield had small changes to the dot product. We knew the page curve would have to keep rising. We computed, it does rise. The only thing which falls is the guy which is not the page curve, which is not the correct Renyi entropy. So if you take the wrong Renyi entropy, it will come down. And so what he told us is the rules are that you use the wrong Renyi entropy because the effective theory, so when you go to in the exact theory, use the correct Renyi entropy, but he says we don't know how to do the calculation. In the effective theory, you have supposed to use this wrong Renyi entropy, which has the extra piece, and then you ask him, why does the effective theory give you the wrong Renyi entropy? And the reason given for that is that when you take effective theories, things far away which were factored can get correlations. I don't see how that happens in any EFT, though it can happen in ensemble averaging, as we well know. He's saying it happens in non-ensemble average theory because gravity is special. This is the entire discussion, and I don't believe that.
Yeah, I just wanted to know how you did this calculation, because there is a UV divergence in the entanglement entropy, right?
Yeah.
So what did you do with the UV divergence?
Yes, so that's a standard problem, right? That you could ask even in anything, like you can ask what CGHS did, right? That way.
Yeah, but I'm just saying that couldn't change that rule.
Yeah, so the point is that once these guys are at infinity, because here it is flat space, right? So in flat space, there's the vacuum and then there are bits over it.
Yeah.
So what we compute as entanglement in the lab, for example, you can ask what's the meaning of having 2 electrons here and saying that entanglement is log 3 or whatever, right? So that simply means it's the entanglement of the excitations. So the entanglement of the vacuum itself is sort of like the energy of the vacuum. You can never actually use it or take it out. The entanglement which you see in the lab, which you actually define for the qubits, is always the entanglement of the excitations over the vacuum. And that is completely well defined in everything. Otherwise,
yeah,
you couldn't
but I'm
even do
just wondering
CGA.
that there is a log epsilon sitting there. I mean, you are looking for, I mean, any possible effect, right? There is a log epsilon sitting there.
Cutoff.
Right?
Cutoff, yeah.
The cutoff. And could it be that that log epsilon, when you change the environment, it changes a little bit?
So I don't think so for the following reason. If that was relevant to the definition of entanglement, you would have the same effect with qubits in the lab. Because when you are this far away, whether this thing is a black hole or this is a star, it doesn't matter. You only see the mass m, right? And so out here, if there was any difficulty in knowing what entanglement was, you'd have the same problem with two experimenters measuring qubits in the lab right now.
Yeah. So you are doing that in an effective field theory, but you are not doing the calculation in an effective field theory, right? You want an exact calculation in this 2D gravity.
Yeah.
See, I mean, there is a difference. So when you do the entanglement between qubits, we are just assuming that all the UV effects are decoupled, right? You have gone to the infrared.
Yeah.
But here you are not doing that, right? You want to have an exact calculation. And so you have to take into account also the UV.
Good. So let's do that. So
right?
I think let's try to put that in explicitly in some mathematical way, right? So you can say the bit here, which you think in this exact theory is, let's say, 1 as opposed to 0, is actually, once you take the semi-classical approximation, it's 1 plus a little bit of 0. So that error can happen.
No, I'm not thinking in terms of bits. I'm just thinking in terms of the cutoff. There is a log epsilon sitting there. And when the background is changing, imagine that the black hole is evaporating, the background is changing.
Yeah.
And how do you know that that log epsilon remains log epsilon and it doesn't get affected?
Yeah, so I think there is some confusion here which I'm not getting. I know you mentioned this to me once long ago, but I don't actually understand that. So let me just show you something which could be some relevance to what you're asking.
See, you want to put it on a computer, right?
The CGS model I want to put on, that will be the exact answer.
But that has a log epsilon.
That has a log epsilon,
yeah.
But I'm saying that the entanglement which you measure from that, it will have a log epsilon you have to worry about. But once these bits go far enough away, I was saying it doesn't mean anything. It won't do anything.
I think, don't you have to specify the UV cutoff before you can actually put it on a computer and do this calculation?
You can, because that came up even when we compute the entanglement of bits in CGHS long ago, right? So we compute the entanglement.
That's a low energy calculation, right? You are not doing a low energy calculation now.
No, it was exact. In the old CGHS model, you exactly quantize gravity because it's a conformal theory, because it's the Liouville mode. So you have the scalars and you have the Liouville mode and you exactly solve it, it's just a CFT. At infinity, you collect lots of photons, right? The entanglement of those photons with what was inside was explicitly computed, right? It was an actual entanglement computation in CGHS without ever trying to make a low energy EFT.
Yeah, but I'm just, see, that on top of that, there's also a vacuum entanglement, right?
So all I'm saying is there's a very easy way to split them and it doesn't create a problem, but maybe we can just talk about it separately.
Yeah, I mean, the point is, because the background is changing, I'm not completely sure that it can be split easily.
Yeah, so I do have some slides on it, but I think we're out of time, but I'll show you these when we chat. Okay.
Go on, we got 2 minutes. Okay. Any other quick questions? Okay,
Can I just
Yeah.
I just want to understand, I think the spirit of the talk was that there wasn't, that all this progress is not actually progress, or at least that's the spirit that I got.
Yeah, the spirit is that I haven't been able to extract the progress.
Okay, good. But I think, correct me if I'm wrong, do you agree that the calculations using Euclidean saddles in which you allow gravity to have topology change in your EFT give correct predictions for the page curve, for the 2-point function, so on and so forth? Is that not progress? Because in my opinion, getting saddle points in Euclidean signature that correctly reproduce all the phenomena that we're interested in and that were problematic in the past, to me, that counts as progress.
So I'm saying that calculations are incorrect. So I'm actually saying the
No, but
calculation
like
of the
you
page
didn't
curve is
explain
just
how
wrong.
they're incorrect.
So I
you
did,
just
right?
explained that you didn't like topology change.
No, no.
That's
No, I love topology change. That's
Okay.
not what I said at all, right? I just said if you try to say that this topology term, which I add, is basically coming from something in the effective theory, I'm finding that when you try to compute a second Rényi entropy, doesn't matter how hard I look, that term doesn't come in the low energy theory. That's what I'm really claiming. People are saying that you write the exact Rényi entropy, in the low energy EFT, I need to add this other saddle point, and I'm saying I don't see that. That's really what I'm saying. So I'm saying it's become a circular error. They've added a term which should not be there. If you add that term, I just showed you why it comes down. I'm just saying it's coming down for a wrong reason. That term is not there. All the three ways I produced of going through it, I couldn't find why that term is there. And I'm just
what
saying
about
if somebody can
since there
tell
was
me.
a talk here yesterday about bag of gold geometries with a count that has very similar wormholes to the ones that were relevant to this computation.
I have the same
Do you
problem.
disagree? Yeah, so what's the
completely
problem with the
disagree.
calculation from yesterday? Just since,
Yeah.
there was an actual talk, we can comment on the talk.
So the talks had the same issue, which I also keep mentioning to Balasubramanian once in a while when he gives us a similar issue in talks. If you actually believe what is being said there, you run into the following problem. So there's a simple bag of gold you can make in the black hole in the following way. So the black hole which you write, as you know, if you just write the black hole enter set coordinates, this is r equal to 0, this is r equals 2m, and then the good slices look like this. You know they are t equal to constant outside, but they can be taken to be r equal to constant inside. Is that familiar to everybody? Okay. So this, in fact, is one way of writing the bag of gold, right? Wheeler's bag of gold can just be that you can make an infinite big slice inside, and then you can put lots of states here because you can put particles of positive and negative energy alternately, and this is one version of the bag of gold. Let me just do that. Okay. Suppose somebody says that I can't have a very infinitely long slice. After some time, the information here repeats from here, repeats from here. Okay. That's the prediction that they are making, that you can't have once it becomes bigger than roughly S.
I don't think anyone made that prediction. I wasn't here yesterday, but I wouldn't say that at least the literature that I know makes a prediction that
So
the bag of gold
I
cannot
thought
be
these states were
infinitely
not supposed to be orthogonal. You can make infinitely many states here because each of these can be 0 or 1.
Well, here you're writing down a single state. You're writing down one slice,
Yeah.
so which is one state in gravity. You could draw a different slice with different matter excitations, and we can talk about the inner product between the states on those two slices.
We can. I just wrote this down as an example of the bag of, there are so many constructions of bag of gold. Let me just take one for the moment because I'm just making an abstract argument. Then we can go back to your argument. Suppose you take this state, you can easily write infinitely many states, and this just came all the way back from Hawking's puzzle, right? Because you can keep throwing matter, evaporating the whole, throwing matter, evaporating the whole. You can hold infinite amount of entanglement, and the reason is that you have these states. So now you would like to argue that once this slice becomes longer than some power like of e to the s, the states start repeating. They're not actually all orthogonal, even though they look that they are all orthogonal. Okay, suppose someone were to say that. It's something very funny, because if you just take this piece and you just ask what this geometry looks like, the time evolution now is in this direction. This is actually a one-dimensional cosmology. So you must have heard it also from GR talks. This is a cosmology which is like a cylinder if you draw the angular part also. It's just a one-dimensional cosmology as a cylinder. Just forget everything else, just a one-dimensional cylinder. There's the angular circle, S2, which wasn't drawn, and it's like this, is evolving in time like this towards a big crunch. Okay, just a one-dimensional cosmology. And it's just heading towards the big crunch. It's a homogeneous cosmology. Okay, if I were to believe what they say, which actually I don't, you'd have to say that if I gave you a very long infinite cosmology, the states in this region actually are not orthogonal to the states here, and so in fact you cannot have more than a certain number of states given by the width of the cylinder on this circle. Okay, let's see how many people would believe that. If you took this over to the GR community and you said in our cosmology, the states in one region are not give a finite number, so an infinite cosmology cannot have an infinite number of states. It's the same. I'm forced to that conclusion if I take this solution to the bags of gold.
I'm sorry, I'm asking about the talk yesterday. I don't think the talk yesterday talked about these cosmologies. So if you can point to what was wrong with the wormholes in the talk yesterday, that will be a bit better, because if you're bringing up a puzzle about another geometry,
no, I agree.
that the calculation
Okay,
from
this is what should tell, okay, this can only tell you that you should question it. But the error, I think, is the following, which is being made in all these papers. It's the fact that they all use the wrong dot product for gravity. So the dot product has the following error. It's the same error of joining things which are actually not joined. So if you look at a slightly earlier paper of Balasubramaniam, which is much cleaner in understanding the dot product issue, if you take two disconnected systems, which have nothing to do with each other, okay? But you say this is gravity, so there's initial state, final state, initial state, final state, but they have nothing to do with each other, okay? Should you have, when you compare dot product of this with this, should you have things that actually go across as well? Okay. Now suppose these two systems are coming as two replicas of one system. Now replica is a mathematical trick. Gravity is just a bunch of, for me, gravity is just a bunch of fields with some rules. If I have a bunch of fields with some rule, I make a replica for the replica trick. The replica trick, we all know, it comes from StatMech. If you make a second replica of something, if you now suddenly jump up and say, in gravity, the rules are not that this guy dots with this and this guy dots with this, but this guy can also dot with this, I need to know where it's coming from, because I don't think it's there. And all these people are putting it there, and they're getting a wrong dot product. And once you make one mistake, you can keep making mistakes. And all the mistakes are all coming from this place. The second thing that they're doing in the replica wormhole, the one I was complaining about, the one in Barcelona's paper about the universe, the one in the dot product they're using now, they're taking two different replicas, and they are saying, because this is gravity, I can join one replica to the other. And I think, no, two different replicas in any unitary theory will have to be orthogonal. And they're saying in the semi-classical limit, sometimes it's semi-classical limit, sometimes it's because of gravity, they're joining them across. And I would love for someone to explain this to me. See, I could well be wrong. I just want to be very emphatic because I want to be saying what's bothering me for so many years. So just because I'm emphatic doesn't mean I'm correct. But please tell me what could be wrong with this.
I think we should probably finish there. Samir has stood up in front of us for 2 hours and taken incoming fire. I think we should really thank him for that.